Turns out that pH is fantastically important for any number of aqueous reactions, in particular biological reactions. Many reactions won't occur, or the proteins will denature and stop functioning if you exceed a very narrow range of pH values. And when we're performing reactions in the laboratory, if they're sensitive to pH, we also want a way to control the pH so that it doesn't upset our chemical experiment. Well, the solution to keeping the pH from changing too much, just because you've partaken of a little bit of orange juice or a little bit of Alka-Seltzer, is we can use Le Chatelier's principle. So Le Chatelier's principle told us how we could predict the minimization of change when a system responds to a disturbance. And so we can set up our system so that the minimization will help us out. So let's say we have this acid-base reaction where we have acetic acid and its conjugate base is acetate. And so we can decompose our acetic acid and produce H+, or the H+ can react with our acetate to produce acetic acid. Well, if we add a base to this, what that base is going to do is react with the H+ and take it out of the solution. So Chatelier says if the H+ concentration goes down here, our reaction will respond in some way to partially offset that, replace some of the H+. And the way it will do that is that some of this acetic acid, which formerly was not decomposed, will go ahead and decompose and produce more acetate and more H+. Conversely, if we add an acid, that's going to produce additional H+. So Le Chatelier says the reaction will do something to offset that increase, and what it will do is some of our H+ will react with the acetate to produce more acetic acid molecules. So the H+ concentration will go down. So that should help to diminish our effects from adding an acid or a base to the solution. But there is a problem with this last case of adding an acid. Remember, weak acids, they don't ionize very much. There's a very, very small percentage of this acetic acid which actually decomposes in acetate. So if we are relying on this acetate to react with some of the H+ we've added, it's going to be a problem if there's not very much of it. So how are we going to get around that? Solution's very straightforward. We just need to add some more acetate. And the way we can do that is we can add a salt, such as sodium acetate, which is going to decompose into the acetate anion that we want, and then also some neutral Na+ that we don't really care about. So this is an example of a buffer. It's a mixture of a weak acid or a weak base and its conjugate, and it's going to be able to resist changes in pH to our system. So, for example, your body is a heavily buffered system, and so when you drink a glass of orange juice, it doesn't go off kilter. The pH will remain very stable and not be altered by the presence of that additional acid. So an example of calculating the pH for a buffered system, let's say that we have 150 milliliter solution of 0.1 molar acetic acid, and to supply our additional acetate anion, we'll go ahead and add 5 grams of potassium acetate. Since this is an equilibrium reaction where we have a weak acid, we're going to need to solve an equilibrium problem. And first thing that we're going to do is we're going to find the initial concentrations that we can plug into the first row of our ice table. We'll need to convert our 5 grams of potassium acetate into a concentration then. So divide by its molecular weight to get into moles, then divide by the number of liters of solution we have to get into molarity. So we have 0.3 molars of potassium acetate. And here I'll just be a little bit explicit. So our potassium acetate, this is highly soluble since one of the ions is an alkali metal. So it will dissociate almost completely into acetate and potassium. So we'll have a 1-to-1 ratio of acetate to potassium acetate. So our 0.3 molar solution of potassium acetate becomes a 0.3 molar solution of acetate. We can then plug that information into the first row of our ice table. We have 0.1 molar concentration of our acetic acid, and we figured out that we would have a 0.34 molar concentration of our acetate. And we'll assume we have approximately no H plus at the beginning, other than that which the ionization of water contributes. And we lose a mole of acetic acid and gain a mole of acetate and H plus. And so these are our final equilibrium concentrations. So we'll go ahead and plug in now to the equilibrium expression, and I've looked up the Ka value for acetic acid in a table. Found that it was 1.7 times 10 to the minus 5. We get two values for x if we use a algebraic solving system. And we can see that this value must be incorrect because it will give us a negative concentration for H+. So we can go ahead and rule that out. Our concentration must be 5 times 10 to the minus 6 molar for our H+. Then we just need to convert that to a pH. So take negative log base 10 of 5 times 10 to the minus 6, and you get 5.3 as the pH of our buffered system. We have to do calculations of the previous type quite frequently. So you may be very relieved to hear that there's a simple approximation which reduces all that calculation to about a single line of work, just one equation. That's the Henderson-Hasselbach approximation. So to find the pH of our buffered system, we take the pKa of our acid or conjugate acid and add log base 10 of the base concentration divided by the acid concentration. Now first note, these do need to be the conjugate acid and base. This is not a general equation for any solution that you create by mixing an acid and a base together. It has to be specifically a reaction between base and its conjugate acid, and acid and its conjugate base. And you do want it to be the initial concentrations here. Don't go trying to figure out what the final concentrations are. At that point, you've already solved the problem. This approximation is trying to save you from having to do all that extra work. And also note that since the volume is the same for this base and this acid, this is moles over volume, this is moles over volume, and they're the same volumes, those volumes will cancel out. So if you know the moles of your base and you know the moles of your acid, you can actually just go ahead and stick the moles in here without converting it to concentration. And here I've also given you this expression if you want it for POH. So that's just equal to the pKb plus log base 10 of what will now be the acid concentration divided by the base concentration. Now as with any approximation, there's some caveats to using it. This is only going to be accurate if our pKa value is between about 4 and 10. We don't want to have too strong of an acid or too strong of a base. We want our acid and base concentrations to be fairly similar. So say you don't want more than a factor of 100 difference between them. And you don't want to have it too dilute or too concentrated. So somewhere in the range of about a millimolar to a molar. Now, since we're considering 3 criteria, you have to kind of take a holistic view to this. If you're really spot on here and really in the middle here, you might be a little bit more tolerant about deviating out a little outside of these boundaries here. Conversely, if you're right on the edge of all of these, you might have to consider that you may not be as accurate as you hoped. But if you're dead on the middle for all of these, then you're good. So for example, let's go ahead and revisit the problem we considered previously. Find the pH of a solution that is 0.1 molar acetic acid and 0.34 molar acetate. First thing that we need to do is check and see if this meets the criteria for the Henderson-Hasselbach. Well, our concentrations look very good. They're not really concentrated in the 1 molar range. They're not really dilute in the 1 millimolar range. They're not more than a factor of 100 difference. This is about 3 times this concentration. And if we check the pKa for our acetic acid, you get 4.77. So that's also in the range of about between 4 and 10. So this seems like it's going to work out. So plugging in to our Henderson-Hasselbach equation, pKa of 4.77, log base 10 of the base concentration, this acetate, divided by the acid concentration, we get a pH of 5.3. That's the same pH that we got previously, so in this case this is a really good approximation. General approach, which is going to work for all of these buffer problems that you might encounter, is to first work out the initial concentrations from all the strong reactions. So that's where you have a strong acid or a strong base reacting, or where you have something that's strongly soluble, producing ions in the solution. So you could just do some simple stoichiometry to figure out the quantities of all these and divide those into the volume of the solution to get their concentrations. Then your next step, that's going to supply the first row of your ice table if you're using the ice table. But you probably want to check first and see if you can use the Henderson-Hasselbach method because it's simpler. So in general, if the concentrations are roughly similar and it's not too concentrated and it's not too dilute and you don't have a really strong acid or a really strong base involved, then you're going to be good to use the Henderson-Hasselbach. In every other case, you want to use the ice method that we used previously. So for example, let's go ahead and take our solution we had previously, 150 milliliters, that's 0.1 molar in acetic acid and 0.34 molar in acetate, and add 3 milliliters of hydrochloric acid, 0.2 molar, which is a strong acid. So we want to go ahead and, as mentioned, first work out the initial concentrations that result from our strong reactions. And this is going to be our strong reaction. We have a strong acid, and the acetate anion is a base in this case. So these will react to produce acetic acid and chloride ions in our solution. So we want to figure out how this reaction changes the number of moles of each of these substances that we have in our solution. Well, since this is a strong reaction, we know that all of this HCl is going to react here. So I'll go ahead and figure out how many moles of HCl we have, and that's going to be also the change in HCl. We're going to lose that quantity since it all reacts. So 0.2 moles per liter HCl times our 0.15 liters of solution. I've made it negative since we're losing it. Comes out to a change of minus 0.03 moles here for our HCl. Well, because of the stoichiometry of this reaction, that must mean that we're also losing that same quantity of acetate anions, and we'll be producing that amount of acetic acid. Now we can find our new concentrations. So for our acetate, we had a 0.34 molar solution and 150 milliliters of it. So this right here is the number of moles of acetate that we started with. And now we're going to lose 0.03 moles of it in that reaction with hydrochloric acid. And what will remain is 0.021 moles of acetate. And then to get the concentration, divide that by the volume of the solution. So we have 0.14 molar concentration of acetate. And do the same thing for our acetic acid. So we had a 0.1 molar solution of acetic acid and 150 milliliters of it. And then we generated an additional 0.03 moles from our reaction involving HCl. So that gives us a total now 0.045 moles of acetic acid. Divide that by the volume of 150 milliliters. Turns out that we have now 0.3 molar solution in acetic acid. Now we can solve the equilibrium reaction. Now we can use an ice table, in which case you would plug in these two concentrations in the first row of your ice table, but it will save us a lot of work if we can instead use the Henderson-Hasselbach. So let's see if that applies here. Well, our concentrations, they're pretty reasonable, and our pKa is between 4 and 10, so that checks out. So let's go ahead and try the Henderson-Hasselbach. So pKa plus log base 10 of our base concentration, the acetate, divided by our acid concentration, the acetic acid, and we get a pH of 4.44.